So we finished the last lecture talking about regular, we did some exercises on regular expressions, I think, and regular languages, and deterministic finite state automata. Now we discovered that there are some problems that cannot be solved with regular languages or DFAs or finite state or regular expressions. So some problems, the structure of some problems is not cannot be expressed by these objects, and some problems cannot be solved by DFAs. Many problems can, but not all of them. And many problems which are of interest for computer scientists are actually unsolvable with just DFAs. You need something more. Now, before we get to see how to solve these problems, what machine we can introduce to actually deal with those problems theoretically, I will tell you about grammars. So what's a grammar? A grammar is another point of view upon languages. Okay? So we remember what languages are. Languages are sets of strings. Okay? And they represent the structure of problems. So all problems can be mapped down, all problems that can be solved by computers, by digital computers, can be mapped down to decision problems and to sets of strings. Grammars, so the grammar point of view is another point of view which is actually, it has been proposed quite recently, in the 50s, by Noam Chomsky. And it kind of revolutionized theory of computation at the time. It was really an explosion of work upon grammars because it's such a powerful tool. So grammar is a concept that you can apply it to all language. And given the language, as we learned from history, is basically the most powerful tool we have. The grammar point of view on languages is an extremely powerful tool to make use of language. So we saw computing machines for regular languages, regular expressions for regular languages, the set representation. Now we're looking for grammars, right? So what's a grammar? Let's say that we have a language, this language here, okay? It's pretty simple. It's on the alphabet of zeros and ones. And the language is a set of all strings which start in 0, 0. Okay? How do we represent that as a grammar? So this is a grammar. So a grammar generates a language. If you remember, DFAs accept languages, so you can actually form the language set by establishing what strings are accepted or rejected by a DFA. Regular expression express languages, so that they're a way of describing languages. As I show in the podcast I uploaded on the portal, regular expressions are nothing but a different way of a different notation for sets. So instead of using set notation, which is quite awkward, you use regular expressions. So it's just a shorthand for set notations. Okay. So you can describe languages. You can accept, reject strings and formal languages, or you can generate languages with grammars. So a grammar is basically, a grammar is formed by variables, these capital letters, by terminals, so these in red, and by rules, associating strings of variables and terminals to strings of variables and terminals. Okay. So I will first show an example of how this grammar works, so you can wrap your head around it, and then I give you the formal definition of a grammar. So we want to generate every string that starts with 0, 0. How to do that? Well, let's generate one to give an example on how that is done, okay? So, you start with the initial variable, which is in blue here. So, A is the initial variable, and you substitute it with what you find on the right-hand side, okay? So this rule here is just really rewriting, a symbol rewriting, term rewriting expression. So you have this A, well, I'll just do, okay. So this A becomes 0B for the first rule. This 0B becomes, well, 0, 0, C. So why 0, 0, C? Because you're substituting this B with 0C, right? So you have 0, 0C, 0, 0C. Okay, you see how it works? And just substitution of the terms. So here you have, well, let's generate one string which starts with 0, 0. So, well, for example, a string which starts with 0, 0 is a string 0, 0. Okay? So we see that here we have a rule associating the variable C to the empty string. What does it mean? That here, this 00C yields 0, 0 empty string, which, you know, is the empty string, so we just delete it, and that's 0, 0. You see how it works? Well, let's derive another one, just for good measure. So instead of deriving here, instead of yielding the empty string, let's yield 0C. Okay, so we have 0, 0 and 0, C. Okay, and maybe this 0, 0, 0C will yield 0, 0, 0, 1, because here we have this rule here. We can substitute C with 1C, okay? So 0, 0, 0, 1, C, C, and this maybe will become the empty string, so you end up with 0, 0. Well, you see that all strings that start with 0, 0 can be generated by this grammar, right? Because you just, if you want a 1 here, you just put 1C, and then maybe you end up, you end with an empty string, or maybe you want to add some other binary digits, and you can just continue doing 0C, 1C, 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 0C, 1C, and then at the end terminate with the empty string. So that's how grammar works. Grammars tell you how to substitute variables, basically, okay? So tell you how to generate strings starting from some starting variable. And now for the formal definition. So, a grammar is a for tuple. So you have 4 objects. If you have those 4 objects, you have a grammar. Okay? So, you have a set of variables, V. So, what's V in the previous example? What's the set of variables here? Come on, I even color-coded it.
B, C.
B, C? And
C, C, C.
Well, no, well, we're just looking at the actual grammar, not the derivation. So you have A, B, and C, basically. Okay? So that's the variables of the grammar. A, B, and C are the variables. You have the terminals. What are the terminals? Well, the terminals are the actual symbols which will compose, which will form the string in the end. Okay? So what are the terminals here?
0 and 1.
Exactly. So we have 0 and 1. So the rules. The way, okay. First, I want to explain you this terminology here, okay? So this is actually really similar to regular expressions, right? It is actually set notation, so they're really similar. So what does it mean? A rule is something which relates. So which goes from a, okay, how to read this? Basically, you have here you have to have at least one variable. Okay, so you have to have at least these, and the variable can be can be preceded or followed by a string of variables and terminals, and from that you get a string of variables and terminals. So in this case, this means that, for example, 1 0 A C 1, for example, and A, I don't know, yields 1 1, I don't know, B. This is a rule. This is you know, it responds to the definition. Okay, so this is a proper rule for a grammar. Very complicated, but it's a rule. Okay, so here the important thing is that you have at least one variable, and here you can have whatever you want. So you should be able to read this notation here, right? Because it's very similar to regular expressions, and we saw that. So this is a set of terminals. The rules. So we represent the rules as tuples, okay? Because you relate something to something else. A rule of the original grammar will be A, 0, B. This is a rule. Then B, 0, C. This is a rule. You see that? So you see A, 0, B, just because here you have, say, A, 0, B. Okay? So this is how you represent the rules in set notation. You have others. What's the start variable? What's the starting variable? A. A. Oops. A belonging to B, meaning that it is a variable. Okay? So this is the formal definition of a grammar. And this is the most general definition, meaning that you really have many grammars. You have regular grammars, or actually called linear grammars. You have context-free grammars, context-sensitive grammars. You have many grammars. Okay? This is the most general definition, meaning that if you have something in your hands which responds to this, that is a grammar. You can say this is a grammar. Now, the specific grammars add specific conditions to this definition here, and we will see that. So, first of all, let's relate this grammar concept to something we already know, okay? So, what we saw here, this thing here, is called a left linear grammar. Left linear grammars modify the definition, the original definition for grammars, by saying, okay, you cannot have whatever you want before and whatever you want after. You have to add just a variable on the left-hand side in a rule, and a terminal followed by a variable on the right-hand side. Actually, you can also miss the variable. But the important thing is that if you have a terminal and a variable, they're in this order, and you cannot have anything else. Okay, so this is the form of a left linear grammar. Left linear because the terminals are on the left. There's actually right linear grammars, and they're exactly equivalent, so we will stick with left linear grammars. Okay. So what's interesting about left linear grammars? Well, they generate exactly the languages that are recognized by NFAs, non-deterministic finite state automata, which we know to be equivalent to DFAs, deterministic finite state automata, which we know being accepting regular languages. So what does it mean? That if you have a regular language, you can express it with a left linear grammar. Okay? That's pretty neat. It's another point of view on languages, which can be really useful. Okay? it is actually quite easy to convert from a left linear grammar to a DFA, or sorry, to an NFA, which can be then converted if you want to a DFA, okay? So for example, let's take our original grammar of strings starting in 0, 0. How does this work? Okay, then, you have a set of states, which is exactly the same as the set of variables. So you have a state A, then a state B, and a state C. Okay? So state A is your starting state, because it's the starting variable in the grammar. State B, and state C, which is the final state, because it ends with a terminal. At a certain point, you cannot add anything else. That's the accept state, because if you reach the terminal, then you're done. You generated this string. So 0b, the first rule is A to 0b. Well, it's simple. It's just 0. Okay. Second rule, B 0c. You go to C, you put a 0. C 0c, you have a 0. C 1c, you have a 1. C empty string, you don't need to do anything. So this is clearly the DFA. We were lucky, this is a DFA, not an NFA, so we ended up with something deterministic, but it's not always the case. So it's clearly the DFA recognizing the strings which start in 0, 0, right? So 0, 0, and then you can have whatever you want, 0, 1, okay, it doesn't matter. So your string is accepted as long as it starts with 0, 0. So this is nice. Why are these left linear grammars equivalent to NFAs and not, well, they're equivalent to DFAs, but why, when you do the conversion, you most of the time end up with an NFA? Because grammars are naturally non-deterministic, okay? Meaning that you can have, for example, a rule saying C0C or a rule saying C0B, okay? So you have C0C, oh, I'll just write it down. So if we had, for example, come on, okay, 0B here, and maybe 0C. Okay, what does it mean? That after you generated a 0, maybe you will generate a B, and whatever it yields, or is yields the right pronunciation? Yes, okay. So whatever it yields after B, or you can have a C and whatever it yields, okay? So the fact that you have a 0 doesn't tell you how it's going to end. It's non-deterministic. In fact, if I have to convert this to the DFA, so sorry, to the NFA, so I have a C 0B. Well, I don't know. Yeah, I don't think you will accept anything now. Well, 0, and then I have C 0C. Well, okay, let's say that we have something here to get to C, okay, just to say. So, if I do 0 and 1 and 0, this is non-deterministic, because here, when I input the third symbol, 0, one process, let's say, goes to B, and one process stays in C. So it's non-deterministic, because you have the same transition, the same symbol in two transitions starting from the same state, okay? So, other examples of this, let's transform this DFA into a left linear grammar. Well, it's really easy again. So you have, so I want you to help me out. So what's the starting variable of my left linear grammar for this DFA? Exactly, very good. S. Where does S go?
1S.
1S, perfect. 1S. Then?
S goes to 0A.
Okay, see. You got it. 0A. Oops. Okay. Then you have
A1A.
A1A, exactly. A1A. Then exactly. A0S. Well, yeah. So this grammar, what is this grammar generating? Can you explain what this is doing in English?
It's accepting a 0 and a 1 as the final state. So it's like 0 and then any number of ones
Has to end in 1.
isn't it? So it has to end in 1.
Well, it's
So if it's S, it doesn't. If it's 1, it doesn't move forward. If it's 0, it does.
yeah, you're actually right. Yes, it's exactly that. Yeah. Yes. There's also this property that you have to have only odd zeros, right? Yeah, because you can end with 1 here, right? So you have odd zeros and it ends with 1. But very good. I had to think about it. So this is the language having an odd number of zeros and ending with 1. Odd number of zeros ending with 1.
Why does it have to end with 1?
No, I think.
It doesn't have to end in 1.
Yeah, just odd zeros. Okay. Yeah, it's just the language of odd zeros. Okay. And this grammar is generating exactly that. So you see, it's really easy to do the conversion. There's nothing to worrying about it. Just to do it, it's easy, but we'll do it the same. This is an NFA. So this was all DFAs. Here you have an NFA, but it is exactly the same, the same procedure. So you have the starting state as it goes to, well, you have A, and you go to S, or you can do S. What happens here?
Beta X.
Sorry?
Beta X.
I think it's empty string.
Is, well, yeah, no,
It
well,
looks like a B.
no, here is empty string, sorry. It's not fantastic resolution. What you have here is just S goes to X. No terminals, because of course, well, you could put the empty string, but of course it's the empty string, so it doesn't matter. So here you have X. Well, you see where this is going, right? So you have X going to BX, and then X going to Y, and then Y going to CY, and then Y going to empty string. So you make sure that's the, at the end of the string, you don't have to put any more variables. You end up with the empty string, so you have a string of terminals, and that's the generated string. Okay? So quite easy. So, let's see if I forgot something on the way. I think I didn't. So, there's where we are now. So we introduced grammars, and we saw the linear grammars, and how they generate exactly the regular languages. So they generate all the regular languages. And so they accept, they generate the sets that DFAs accept, okay? So we're here, but there's much more to grammars. So this set here, so this is actually an improper kind of set, because I'm putting languages, machines, and grammars in the same point. I color-coded them, so it's like you have the set of regular languages is contained into the set of deterministic context-free languages is contained into the context-free languages. The same DFAs are a special case of deterministic push-down machines, which are a special case of non-deterministic push-down machines. Linear grammars are actually deterministic context-free grammars, or LRK grammars. They have this name. Do you know the LRK parser? No. Well, it's a very famous parser to parse programming languages. Okay, I think it was the creator was Donald Knuth, which is a very famous programmer. And well, when he invented it, when he discovered it, it was had a revolution in parsing theory. So. Linear grammars are a special case of deterministic context-free grammars, which are a special case of context-free grammars. So, we will now have a look at context-free grammars and context-free languages. Why are they interesting? Well, they're really interesting. Because many programming languages are context-free languages. And with context-free grammars, you can build a grammar for the languages, for the programming language, and that means you can build a parser, which parses the language. So what happens? Well, Java, for example, is an example of a context-free language. Apparently, it's quite hard to actually be sure about that. But many people think it's context-free, and in the Oracle website, you can actually find the grammar. Okay, this is a grammar. Instead of having the arrow, you have your, the column. Instead of having, the variables with capital letters, you have these names, these variables. So this is a grammar. Java actually has a grammar, and the parser uses that. And so this is the whole process going from code to machine language. So you start with code, then your code goes through a parser. A parser is composed by a lexical analyzer, or lexer, and a syntactical analyzer. Okay, what does it mean? At this level, you have DFAs, let's say DFAs, trying to extract tokens from your code. So for example, a DFA recognizes, oh, there's an if here, there's a while here, there's a list here. So the lexer produces tokens, okay? Let's say, okay, if, while, these are the keywords. And it passes the tokens to the syntactical analyzer, which makes a parse tree. We will see that in a second. A parse tree out of the tokens, meaning that it actually builds. It actually tries to figure out what the tokens, the order of the tokens mean. What sentence is the language expressing? Okay, using the grammar. So you parse using the grammar. Okay, and actually at this level you normally have context-free grammars, which we will see in a minute. So the syntactical analyzer builds a parse tree. So let's say it assigns a meaning to all the statements. Let's put it that way. Well, meaning is just labels actually, not philosophical semantic. So it produces a parse tree, and then the compiler grabs this parse tree and makes it into machine code, okay, machine language. So that's why what we're studying is relevant. Okay, at every level of that, you have an application of computation theory concepts. So specifically, we will see this today, context-free grammars. What time is it? Oh, okay. So let's return to this, context-free grammars. So what's a context-free grammar? Well, a context-free grammar is a grammar generating context-free languages. And context-free languages are interesting because they're more powerful. They express a wider range of problems than regular languages. So if you're, did I do the example here? Not yet, okay. We'll see it in a second. So well, first let's have a definition of grammars. of context-free grammars. Okay. So what's a context-free grammar? It's a grammar, and instead of having one variables with something here, going to a string of terminals and variables, what you can have is just a variable on the left-hand side, as a rule, variable on the left-hand side, and on the right-hand side you can have whatever you want. Okay, so this is a context-free grammar, as opposed, for example, to linear grammars. If you remember, in linear grammars, you could only have variable going to terminal followed by variable. Okay. So this is the definition of a context-free grammar. So the interesting thing is that as soon as you build a grammar, as you have a grammar with a rule which is not in this form here, so terminal followed by variable, you're not generating a regular language anymore. You're generating something more. So you're generating something that cannot be expressed by a regular expression, that cannot be accepted by any DFA, and it's not a regular language, okay? A non-regular language. So, for example, you should remember, well, let's first generate some strings. This is a grammar. This is a context-free grammar, because you see here you have terminal, variable, terminal. This is not left linear or right linear, it's something else, it's context-free, okay? So what strings can we generate with that?
S0, S1.
Sorry?
So you've got S goes to 0, S1, or S goes into empty string. Is that an or is that concatenation?
Yeah, sorry, yeah. Now, instead of writing S goes to something, then S goes to something else, then S goes to something else, I just put an OR, okay? This is just syntactic sugar, okay? Just to make things more tidy and understandable. So this is a logical OR. I'll write it down. So logic. We saw that in the last lecture, but okay? So, let's generate some strings. So, for example, this is a derivation. So 0, 1 is a string in the language. Okay? The string generated by this grammar. You see what's happening here? So because S yields 0, S1, that's exactly what I'm doing here. I'm substituting this S with 0, S1. And then maybe this can go to the empty string, and then you get 0, 0, 1, 1. So you see where this is going, okay? If we continue, we can produce this string here, this string here. So what language is that?
Begins with 0 and ends with 1.
Sorry?
0 and 1, and it begins with 0 and ends with 1.
Well, half always have to be 0 and half always have to be 1.
That's true. So you have to have the same number of zeros followed by the same numbers of ones. So the language is, well, let's write it in set notation. Rows equal to 0 to the n, 1 to the n, and n is a natural number, so 1, 2, 3, 4, 5, etc. Okay? So, but if you remember, we already met this language here when I showed you that some problems cannot be solved by any DFA. Okay? This is the language I used to prove to you. I use this language as an example to show you the pumping lemma. Okay? So because this language needs something that can count as a machine. We won't be talking about the machine today, we will be talking about the machine in the next lecture. But because it needs something that can count to infinity, basically, okay, so it doesn't have to, so it needs something that has unbounded memory, okay? DFAs don't have unbounded memory, they have a finite amount of memory, so this language cannot be recognized by any DFA. But it turns out it can be quite easily generated by a context-free grammar. So that's the beauty of it. So the context-free grammars have this recursive nature. Okay? So you get that S, the sum to 0 and 1s, that S 0 and 1, 0 and 1, 0 and 1 is like, it's a recursion, right? It's a recursive substitution. And you can get these strings here that you couldn't get in any way in regular languages. And, you know, you can already see, you can model some problems with this kind of language, okay? So, for example, I don't know, let's see. I'm thinking about other languages, but if you jump, okay, if you climb n stairs, you have to descend n stairs to get to the ground. That's something you can use, I don't know, in robotics maybe. So you count the steps, and if your robot wants to go down again and be at the same level it was before, you have to decline those steps. So that's that language. You don't want to care. You know, you cannot use a DFA for that. You have to use this new model here. In this case, we're just looking at the grammar, so how to generate that language. But of course, then we will meet the push-down automata, which will be the machines able to recognize those kind of strings and so to solve the problem. Okay. So this language is regular. You discovered that context-free grammars, or C, F, G, have a recursive nature to them, and that's what makes them able to generate languages that are not regular. You don't have a recursion in regular languages, okay? So, oh, this is a nice example. It's a pity that this projector is a little small. So, this is the grammar of balanced parentheses, something that every IDE has to work out somehow, okay? So if you want an IDE telling you, hey man, you missed a closing parenthesis here, you have to implement this grammar somehow, okay? So this is the grammar of closing of balanced parentheses, and so we need this rule here and this rule here, because with the first rule you get exactly the language I showed you before, okay? So you get 0, 0, 0, 1, 1, 1. And then of course we're happy with that, because it's for each 0, for each open parenthesis, you have a 1, a closed parenthesis, so they're well balanced, so that's something you want to produce. But of course, this rule alone doesn't permit something of this form, 0, 1, 0, 1, 0, 1, okay? Which will be something like open, closed, inside, open, closed, okay? That's something you want to produce, and that's made possible by this rule here. S equal to, you know, S yields SS. Okay, this is SS in a way, or maybe. So, what kind of strings can we generate with it? Well, let's do some derivations. S, for example, you tell me what rule to apply so we get a string. Tell me one. Not the empty string.
SS.
Okay? SS. And then I make a choice and I do SSS, meaning that I split one of the S into S's, so I get 3 S's. And then maybe I'll be happy with that, and I'll, for example, let's see. Well, let's just do this. So, okay, we do the derivation in, just do this. Okay, so this is a string which is a is generated by the grammar. Okay, so each of those became one of those, and then I substitute the S for an empty string. Okay, just to make things faster. Otherwise, I have to do a really long derivation. Okay. Another string that can be generated with that grammar is, well, you get where I'm going, right? 0, 0, 1, 1, for example, is another string generated by the grammar. So you have S, 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 S. So you have two S's which split. I don't want to do the derivation, but you see, it's just the grammar of balanced parentheses. Okay. So what if I want to do the opposite? What if I want to be a parser and recognize a string? Okay. Meaning, for example, is this long string here generated by the grammar? Well, if it is, if I think it is, and I think it is, I'm sure it is because I made it, the grammar must be able somehow to generate it. So there must be a derivation which brings that string there, okay? So how to go about that? Well, I did it here. Because we're balancing parentheses, so we know what's the meaning of our language, so we can be smart about it. Because it's balancing parentheses, we can just, well, I'll do it again, match nearby zeros and ones, which will be the most nested parentheses. Then we go outside and we do the less nested parentheses and so on. So for example, 0, 1, 0, 1, 0, 1, 0, 1. I missed something. No. Then we go and do 0, 1, because we go up in the hierarchy of the parentheses. And then we go, well, this is another 0, 1, and then we go 0 and 1. And in fact, they're balanced, the zeros and ones are balanced, okay? So, how to make sure that actually, well, we saw that this is the language of matched parentheses, and now we want to generate it with our grammar. Let's derive this string. So let's do the derivation. So remember the rules are S going to 0, S1, or SS, or empty string. Okay? So derivation. Well, we have two blocks of parentheses. So we have a break of pattern here. So what do we start with? We have two nestings, one after the other. What rule do we apply as the first derivation? So what does this yields? Well, it's SS, okay? Because we're doing, so SS, which means S, S, okay? So we will now unpack this. We will continue to generate the nested parentheses, but we have to start with S, S, because there's this break here of pattern. Sorry. So we start with SS. Then inside here, how many S's do we want inside here?
3 inside the
4. Well, yeah, but just for now, let's stick to 3, and then we generate the fourth one, okay? And here we want another S. So SS, the first S we want to be other 3 S's. So well, let's start to unpack the second one so we don't get confused. So this S, we want it to contain another S, and so we do this. So this becomes 0S1, becoming S, sorry, 0, 0, 1, 1. Okay? So we have generated the last bit of our string, which is this one, okay? 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. you could have noticed that here, and actually here, I had two choices. I could derive this first, or I could derive this first. Or here, I could have derived this first, or this. Okay? So I have a choice. To keep things tidy, let's say, we can stick to a derivation. So if I wanted, for example, I could have stuck with a leftmost derivation. So I always derive first what's on the left of my string, okay? Or I could do rightmost derivation, but I will do. Well, in this case, it doesn't really matter what. But sometimes we want to stick to a derivation so that we can say, okay, these two strings have the same leftmost derivation. Okay? So they are the same string. Okay? So if we continue, then this becomes two S's, this becomes two S's. What I'm doing here already is using a parse tree. Okay? Because I'm tired of doing derivations, and there's a nicer way to visually represent the production of the string here. So this is a parse tree is something like that. S going to S. Let's make them a little bit farther apart. S. S. The second S becomes 0 S1, and this becomes 0 S1, and this becomes the empty string. So we'll now make it more visible, the fact that we're generating the second part of our string. Okay? Let's continue here. So we want 3 S's, right? Yes. So what we can just do 0 0 1. This is an S, and then here I can do S S, and this one is split into other two S. But why I'm doing that? Because this way, in the end, we get 3 S's, right? So we have 0, 1, and 3 S's. And then I split the middle one into, well, 0, S1. Okay, you get the gist of it. This is a parse tree. I think it's pretty clear how to use the grammar to get a parse tree. Now, there's something peculiar about this parse tree here. The fact is that to get the 3 S's that I need to represent the 3 nested parentheses, I could have chosen this one instead of this one. So instead of splitting this into 2 to get 3 S's, I could have split this into 2. And with this one getting 3 S's, okay? That's problematic, meaning that with the same parse tree, well, actually the same string can be represented, can be generated by 2 different parse trees, okay? So you have the same string and 2 parse trees. As you can see here, the derivation, if it's leftmost or if it's rightmost, doesn't matter, because that representation it doesn't enter the parse tree. So here, if I start deriving this one first or this one first, it doesn't matter. At the end, the tree will look exactly the same, right? But it turns out, so if you have 2 parse trees for a string, that means your grammar is ambiguous. Okay? So it is famous optical illusion. Some of you will see a rabbit, some of you will see a duck. If you see a duck, then you are a psychotic homicidal maniac. You see a duck?
I see a rabbit.
Okay, cool. So, what's the deal with ambiguous grammars? Well, ambiguous grammars, you can get different parse trees for the same string. And that's the problem when you want to parse, for example, a programming language. Why is that? Because when you parse your programming language, the way your parse tree looks gives you an operational meaning of what your code is telling to the machine, okay? So it's like, you know, okay, I have to remember this sentence. The girl looked at the man with the binoculars. Okay, the girl looked at the man with the binoculars. Is the girl looking at the man with the binoculars, or is the girl with the binoculars looking at the man? Okay, as you see, this is ambiguous. So you get this ambiguity also in natural language. Whereas, okay, in natural language it could be okay. In programming languages, that's really bad because it means that your parser won't know what you mean with your code. Okay? So, this is the definition of ambiguity. So, a grammar is ambiguous if it can generate a string with more than one parse tree. If every string generated by a grammar is associated to a unique parse tree, then the grammar is non-ambiguous, and that's the kind of grammar you will want to use if you want to create, for example, a programming language, okay? So that your parser won't have any problem understanding what you mean with your program, with the code. It turns out that, okay, so you can have a perfectly non-ambiguous language, but you may be creating an ambiguous grammar. Okay? So you have a language that could potentially be created, could potentially be generated by a non-ambiguous grammar, but you're not good enough, or you didn't have enough time to work out the grammar, and you end up generating an ambiguous grammar. But maybe you can solve that problem and create a non-ambiguous one. But some languages are actually inherently ambiguous, meaning that for a certain class of languages, you can spend all your life trying to create a non-ambiguous grammar, but you will fail because any grammar generating that language will be ambiguous. Okay, that's interesting to know. I want to give you examples of inherently ambiguous languages because well, it doesn't make sense. I would have to actually explain some advanced concepts, and that's not the place. I would say let's do a break now. So we were at ambiguity. So what's ambiguity? When you have a grammar which generates a string with more than one parse tree. Why is it bad? Why it can be bad? It's not always bad. Why it can be bad? Because given that you normally use context-free grammars, for example, when you want to design programming languages, you want your parser to perfectly understand what your code is telling the CPU, what you actually want to perform, what computation you want to perform, right? But if a string is ambiguous, if your code is ambiguous, so it has more than one parsing, that's dangerous because the parser cannot just say, yeah, okay, choose this one. Yeah, I think you wanted to tell me this. Yeah, I'll just choose this parse tree here. No, that's not how it works. Like, they're machines, they're stupid. So the right way to go about it is try to design a grammar which is not ambiguous. Normally what you do is design a grammar which is ambiguous and then patch, put patches and tell the parser, okay, when you meet this condition here, maybe treat it like this way. For example, C++ is ambiguous. It's an ambiguous language. If you, some expressions are actually ambiguous given the grammar of C++, right? And why does it compile why the parser is not asking you to actually define that what you want from the code. Because of the level of the parser and the lexical analyzer, the compilers have patches, okay? So the programmers say, okay, this is ambiguous, but if you encounter this case here, do this. So choose this parse tree instead of this one, okay? So, of course, in a wonderful world, you would be really good programmers, and your language would be context-free, and your grammar would be completely unambiguous. But that doesn't happen often. And then because languages are not just an academic exercise in who's a smarter programmer, but you actually have to use it for industry. Often they're not really tidy. There's much confusion. And then you design parsers which have to communicate with the lexical analyzer, like in Python, to guide the lexical analyzer in what tokens to spit, okay, to spit out. But in a wonderful world, you will be able to design fantastic grammars which are not ambiguous, and you will need to patch parsers or any of that. Okay, so let's do another example of an ambiguous grammar, which will give you maybe a more intuitive way of why you don't want ambiguity in your, for example, in the grammar of your programming language. So, this grammar here is the grammar generating the language of chained additions and multiplications. So, what's a string in this language here? Well, for example, 1 plus 5 multiplied by 4 multiplied by 5 plus 7 plus 9. Okay? So it's just a chain of multiplications and additions. No parentheses. I think you can already understand why this could be ambiguous, right? So, this is the grammar generating, let's have a look at closer. This is the grammar generating this language here. And what you need as terminals, of course, is just plus, dot, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In our case, we'll just use a decimal system, so 9. Okay. Well, no, actually. Yeah, we just make room for single-digit numbers, okay? We don't do any fancy stuff. So, this grammar generates additions, multiplications, and of course, the terminals. So if I want to do a parse tree for 3 plus 4 multiplied by 5, we have, okay, this is 3 plus 4, so I write S. This is the parse tree, S plus S. And then this S here wants a multiplication, because here you have the multiplication, right? Here you have the multiplication. So here you want a multiplication. You already see where this is going, right? So 3 plus 4, 3 plus 4, 4 multiplied by 5, 4 multiplied by 5. So if I actually, this is nice and tidy. 3, and this is 4, and this is 5. We have these rules here, okay? To make sure we have these terminals. So this is the parse tree for that example, right? S plus S, which is rule 1. The second S becomes S multiplied by S, which is rule 2. And then you put numbers in that, which is the terminal rules, right? But this is not the only tree I can build. For example, I can do something like that, right? It's one rule in the grammar. What will I do now? For example, if I wanted to generate 3 plus 4 multiplied by 5.
Take one of the S's and do the addition.
Exactly. So I take this one, this becomes S plus S, and this becomes 5, and this becomes 3, and then becomes 4, right? This is ambiguous, okay? The same string, two different parsed trees, okay? And you can see why it is important for your grammar not to be ambiguous. Because when your parser is reading, for example, 3, okay, what you give to your parser is the code, right? So 3 plus 4 multiplied by 5. Okay. For example, maybe this 3 is telling the parser that first you have to do the multiplication, and then you do the addition. Whereas this one, you work your addition first, and then your multiplication, okay? And that will have different results, of course, and you don't want that, because how can you choose? So you want to build an unambiguous grammar, non-ambiguous grammar. So I thought, okay, maybe this language is inherently ambiguous. And then I realized it is not inherently ambiguous. The grammar is ambiguous, but the language is not ambiguous. Can you work out why? Why it's not ambiguous? You have the tools to understand why it's not ambiguous. So how can I generate these strings here? Okay. All my strings have this form here, or some, you substitute the plus with a dot, You can build a DFA. You can build a DFA to accept this kind of strings, which is really nice. When I realized it, I felt really stupid because I thought that the language was ambiguous. And I thought that the language was ambiguous because I was giving my meaning. I was applying my meaning to the language. And when you read that, it is ambiguous if you don't know what's the precedence of the operators, right? But actually, I was wrong, and that's another example of the fact that language and meaning are two different things, okay? And you can be fooled by your assigning a meaning to the language. So let's build a DFA which accepts this kind of strings. It's really easy. So you want a number first, so 0 to 9, and then you want either a plus or a multiplication, and well, I think it's just oh yeah, you want another number first. Well, like this, 0 to 9, and this is the accept state, I think. Yeah, this works. I think it accepts exactly the same language. So 0 to 9 plus 0 divided by 9. Yeah, that's it. Does it generate the empty string? No. So this is a DFA generating exactly this language. And DFAs, I actually didn't tell you this bit of information, so you're excused for the fact that you didn't realize that. DFAs can be expressed with linear grammars. It turns out that linear grammars are inherently, so these linear grammars here. So linear grammars are a special case of LRK grammars, and they are always not ambiguous. So LRK grammars, you can, the associated machine is called a deterministic pushdown automaton, which we will see in the next lecture. And if you have an LRK grammar, you're assured that your grammar is unambiguous. It's not ambiguous. You cannot generate ambiguous strings with it, okay? And of course, because a linear grammar is just a special case of LRK grammar, then you know that if you can find a DFA to express your language, to accept your language, your language is not ambiguous. So in this case, the language was not ambiguous, but my grammar was. Okay, that's a nice example of how things go wrong. So, decidability. So I told you that digital computation cannot just answer all your problems, meaning that you cannot just solve all your problems, all the problems you may encounter with digital computation. This is really, really helpful though. Can you read? We'll just try to make it. Let's see if I can like double the Actually better, all right? So, digital computation cannot just solve all the problems. There are some problems for which you would really, really like to have a solution. You really would like to have an algorithm to decide upon those problems. But you can't. You just can't. You just have a general. For example, some questions you may ask: is there a general way to decide if a grammar is ambiguous? That's a really nice question. If you had the answer to that, if you have an algorithm for that, then you could design a language. Okay, you just download software, run it on the grammar language, and your software will tell you this grammar is ambiguous. You cannot, if you want to design a parser for that, you will have to patch things up. You cannot do that. There's no general algorithm to decide if a grammar is ambiguous or not. Actually, I had a thought about it, and it's really mind-blowing, because I thought, well, you don't have a general algorithm to do that, but maybe, you have a collection of algorithms, you solve this one, this class of ambiguous grammars, this class, and then maybe you can exhaust all of them. Well, no, because if you had a class of algorithms, you could create a program, then an algorithm, calling the right one, to solve your specific problems, and that would mean you had an algorithm to decide, right? And this is not true. This is false. So this is really an undecidable problem. So you can never program a software to decide if every grammar you put into the software is ambiguous or not. Same goes for: is there a general way to decide if a language is ambiguous? No. There's no general way to do that. It's undecidable. Is there a general way to make an ambiguous grammar not ambiguous? So we saw that my grammar was ambiguous, but the language was not ambiguous. So you should probably have a grammar somewhere. You have a grammar somewhere which is not ambiguous for not ambiguous language. But you just cannot make a general software which grabs an ambiguous grammar and makes it a non-ambiguous one. Is there a general way to decide if two grammars generate the same language? Oh, this question is not, we're not ready for that. Okay. So, I told you why. Time is it? I told you why context-free grammar is really important. Okay. You design programming languages with them. Actually, I think people were convinced when the context-free grammars came out that our language was context-free, so English or Italian or human language, natural language was context-free. So you could, you could possibly, there was a possibility to design a grammar specifying all possible productions in English, I think there are still some people believing that, but most of them believe that the grammar of natural language is not context-free. It's actually something more. We will see that. So yeah, context-free grammars are such a powerful tool that really makes you want to apply them to everything. So, okay, they're useful. So I want to make use of them. Can I build a grammar? Well, of course you can. It's not as easy as building DFAs, because DFAs are really predictable in a way, okay? But because grammars context-free grammars implement recursion, so you have this recursive nature of grammars, you could find the grammar to be rather unpredictable, so rather hard to understand, how to actually build it. So it's not an easy task, it's an art. It's an art to build a good grammar, okay, for whatever language you want to express, okay, you want to generate. But there are some techniques. So, for example, let's say that my language is the language of strings on 0 and 1, which have an equal number of zeros and ones, okay? This is non-regular, we know that, right? Because you have to count, you have to count zeros and ones. You cannot really, it's not regular. So, semantic technique. It means that I design the grammar, actually designing the variables so that they have some kind of meaning, okay? So I can look at the variables and say, okay, this variable is doing this other variable is doing that. So we want a grammar which generates the language of strings which contain the same number of zeros and ones. Yes. So how to give meaning to this? I already designed it. So for example, we start with S, and let's say we have a 0. Okay? Well, because we start with a 0, we are in depth of a 1, because we want our string to have the same number of zeros and ones. So basically what A is saying is exactly that. So S yields 0, A. A is a variable which gives back a 1. Because you started with a 0, A wants to give you back a 1. And in fact, it does that, right? So you have, let's do an evaluation. S, 0, A. This A becomes 1. So, you see that? 1S. And then maybe S will become again 0A. And A will give you back a 1 to counterbalance this 0 here. So that's what A does. Maybe you want to have 2 zeros or 3 zeros and then somewhere 3 ones, 2 ones to balance. So you have this rule here, because if I just added this one, you could only have 0, 1, 0, 1, 0, 1, 0, 1. In this way here, you double the A. So as we saw in the other examples, if you can double, then you can triple, because we double this one. You can do all possible number of ones. Of course, every time you put an A, you have to put a 0. So in the end, you end up with a balanced, so 0A, for example, let's use this rule here, becomes 0, 0, A, A, and you see that this AA could become 1S, 1S, and then S become the empty string, and then you end up with 0, 0, 1, 1, and it's balanced and you're happy, okay? So the same goes with B, is the opposite, let's say the opposite of A. So if you start with 1, then you want something giving you a 0 back, and B gives you a 0 back, okay? Or 2 zeros if you add 1s, 3 zeros if you add 3, This is the semantic technique. You give your variables an actual meaning, okay? An operational meaning, and so that helps you in designing your grammar. Should I? Another powerful thing that you can use is, of course, recursion, which is the whole point of context-free grammars. I mean, the whole selling point of them, because with recursion you can do something that a regular linear grammars cannot do. So the recursion, how does this work? Well, we want our strings to have the same number of zeros and ones. Then it's like, what you do is you nest 0 ones and 1 zeros, 1 zeros, okay? So what does it mean? I'll show you visually. It's really actually quite uncomplicated. So for example, you can, for example, with A, do something like that. You put a 0 and a 1, okay? And then something in between, that's the S. What's inside? Maybe a B, so it becomes 1, 0, okay? And you're balancing that. Or maybe then, well, you have this rule here which is built so that you can, for example, do, let's see, AB, just AB. So you can, for example, do, you can completely lose the A, and do the B, you can do 0, 1, 1, 0 here, or you see what I mean? 1, 0, 0, 1, for example, meaning that I'll do a parse tree. S, A, B. So when you do the B, you have a 1, S, 0. When you do the A, you, well, let's say, well, yeah, we have the A. We do 0, S, 1, and then S, for example, we can say that is the empty string. So this is the recursive technique. Here you have balanced this, here you have balanced this, but inside you have this recursion, so you can keep adding balanced things. And in the end, of course, the whole string will be balanced because at every step you have added balanced digits, okay? So this is the recursive technique, meaning that here I can do exactly the same as AB, for example, and then do exactly the same. It's recursive, okay? 1, S, 0. This here is exactly the same as this here. It's recursive. Another way to go about it is composing simpler grammars. So let's say you have a problem. It turns out it is a context-free problem, meaning that your language has to be expressed with a context-free grammar. And you think, and you realize, oh, this language, I can actually split it into languages, let's say. I can actually think about it as a production of two grammars. Actually, forget, it's not the union of two languages, but it's the union of two grammars. Meaning that, for example, this rule here will give me balanced strings of zeros and then 1. Okay? This is actually the language of balanced parentheses. Okay? But you have only this, you're forced to have zeros and ones. You cannot have 1 zeros, okay? But you do the other. You have this second grammar, which is like the parentheses balancing grammar, but you just, instead of using 1 for 0 for opening, use 1. And then you can see it's exactly like this grammar here, right? So you nest 1 0 0 1 0 0 1 1 0, and you end up with a balanced thing. Okay? So these are 3 techniques, 3 ways to go about building a grammar. So something to keep in mind if you want to build a grammar. You know, you can use recursion. So if you can think about your problem in a recursive way, then it's easy to build a grammar which does that. If you can think about your problem as being, so you can give a meaning to the variables of your grammar so that it's easy to build the grammar. And you can compose simple grammars because the union of these rules give you in the end a grammar which generates your original language. So, let me have a look. So we talked about grammars. We talked about the linear grammars and the fact that they're equivalent to DFAs, but they generate the language recognized by DFAs. We talked about context-free grammars, ambiguity, building a grammar, and now, do we have time? We do have time for exercises. So these are exercises coming from Michael Sipser book, Introduction to Computation Theory, I think. No, Introduction to Languages and Computation. I don't remember the title. One word of advice would be to actually read the chapters I put on the portal and actually do the exercises at the end of the chapters. If you do that, you'll surely get a really good mark at your coursework and your exam, because that's the kind of difficulty which you will meet in the exam, right? So if you work out these examples, these exercises, you're in a good shape for acing your exam and coursework. So, give context-free grammars that generate the following languages. In all parts, the alphabet sigma is 0 and 1. Okay? So, grammar for A. And the language contains at least 3 ones. Well, that's trivial. Okay? We know that this is a regular language. Do we know that? If I tell you this is a regular language, would you believe me? Come on, it's easy. You can easily... Sorry? Yeah. You can easily build a DFA. Okay? So if you build a DFA, it's regular. If it's a regular language, you can express it with a linear grammar. And maybe if you can be asked to build a grammar, you can first build the DFA, it's really easy, and then build the grammar, the linear grammar out of it, in the way we saw before, right? So, W contains at least 3 ones, meaning that this is your start state, this is your end state, 1, 1, 1, accept, you're happy. Then here you can do whatever you want, you're really happy. And 1, 0, I think.
It didn't say it had to be in order, does it?
Yeah, I have to do the loops here. 0 and 0. And this is DFA. It's really simple, right? So the important thing is that you have 3 ones. You can have as many zeros as you want anywhere. Let's give a name to the states so we can build the grammar, A, B, C, and D for the accept state. So how to build this grammar? We saw that. It's easy. So this is our starting state, so it's also our starting variable. And it becomes... Oh, we're building the grammar for this DFA.
It's 0A or 1B.
Exactly. Very good. 1B. Then B.
B0B.
0B. 1C. C, well, just 0C or 1D. And then D is 0D or 1D or
E.
Very good. The empty string. So we finished, right? If we are in D, we can just accept. So we put the empty string, so we get rid of this variable in the end in our derivation, and we're happy, and we produce a string. Okay. So if you have a regular language, it's really, really straightforward to build a grammar. Okay. Well, given that you're able to build a DFA, but you will. Don't worry. So B. W starts and ends with the same symbol. Oh, this is nice. So W starts and ends with the same symbol. Well, we want something that puts the same symbol in the start and in the end. And then inside you can do whatever you want, it doesn't matter. Okay? So that's a good problem to use recursion, meaning that, well, let's do this. So B, starting and ending with the same symbol. So start variable is S, and S, what do I put it here? So we know that in the middle you can do whatever you want, right?
Oh, so it'd be...
Sorry?
Would it be a number, a letter, a number?
Exactly. So like 0, I don't know, A, 0, or
1B1.
Well, I think we can use A and just make A whatever it needs to be, okay? I mean, the important thing is that we have those ones or those zeros, right? Or I would also say the empty string. Oh, maybe not, no. It depends how we define starting and ending with the same symbol, right? But let's say that we need a symbol, okay? So no empty string. So let's say that A is 0A or 1A, perfect. 1A or empty string, right? So if we want to generate our language, we see we have, well, let's do a parse tree, S, maybe 0A, S, and then this A can be 0, A, maybe, I don't know, we want a 1 after that, so 1, A, or maybe we don't want anything more, so we have the empty string. So here we have 0, 1, but here we have 0, 0, so it starts and ends with the same symbol. We're happy we generated the language. Okay? Really easy one. Okay, let's see. The length of W is odd. Okay, what does it mean? That you can have strings of length 1, length 3, length 5. So you can have a symbol which adds a terminal and a symbol which adds 2. Okay? And you make sure that your generated string has the both symbols, so at least the one which generates one symbol, right? Because we know that an odd number is something in this form here, right? 2n plus 1. So what does it mean? Well, for example, let's say, let's do ABC. I don't know. I didn't really think about it. ABC and no, actually, let's do AB and A generates what? Sorry?
So it could be like 0 or 1, so they're there, obviously, and then or 0 or 0 or 1, 0 or 0.
So A is 0 or 1, and we're good. And B, it's something like 0, 0, 0, 1, or 1, 0, or 1, 1, or it's always that. Yeah. So we're sure that this one generates strings of which are multiple of 2. Now actually, we want to add also BB, I think. Okay? This way we can have 0, 0, 0, 0, for example, okay? 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, whatever you want. The important thing is that it's a multiple of 2. It's a multiple of 2. And we already know that A has a symbol, so that we're assured that in the end our string will be of odd length.
Does it have to be A or AB? Because 1 is an odd number, so it would be the length of it.
Sorry?
Or just a single digit, 0 or 1, would technically be odd in length, so it could be A or A and B.
A or?
So S could be A or A and B. It doesn't have to be AB, because AB has to have 3, doesn't it?
No, because you have the...
Oh, yeah.
So this is C, W, the length of W is odd, and its middle symbol is a 0. Again, we can be smart. So we want our middle symbol to be 0, and then it has to be odd, the string. So what you can do is, okay, you put a 0 in the middle, and then you start adding a couple of digits, whatever they are, okay? So the couple of digits will be even, plus the 0 in the middle will be odd, right? Really easy.
That one above is wrong though. Does 0 count as a odd number?
0.
Because you could have A0E.
Oh, this one.
Yeah.
A0 E. Yeah, 1 is odd. Yeah.
No, it's 0 odd. If A is 0 and B is E, then you've just literally got 0. Does that count as odd?
Well, the odd length, not odd number.
Oh, the odd length, sorry. Yeah.
Sorry.
Yeah.
Okay, so this one was a 0 in the middle, so maybe we have something like this. A Z, just to say 0, B, and then we know that Z is 0, and then I'm missing something. No, I don't like this. We want it to be recursive, so let's say that we have an S here. Yeah, 0, 1, S, or 1, S, 0, or 0, S, 0, or 1, S, 1, and in the end, I think there was a 0 in the middle, so S can be 0, or nothing, not really. So what you do is, if you do a parse tree of this, you do S is equal to 0, S, 1, for example, right? Then you keep adding, S is equal to, I don't know, 1, S, 0, 1, S, 1. Well, in the end, you're always assured that you end with a 0, right? So your string will be whatever you want here, a 0 in the middle, and of course it will be odd, because even, and then 1 is odd, okay? 5 minutes left. So, oh, palindromes. This is really nice. Let's do palindromes, right? So you know what a palindrome is? So for example, Otto. Oh, well, this is Italian. Well, okay, this is a palindrome. 1, 0, 0, 0, 0, 1. So you have a mirror in the middle, and the mirrored string is a palindrome, right? So we want to build a palindrome, only that. Is that only, yeah, okay. Well, this is really easy, right? You should have all the knowledge to do this. S is equal to, well, to be a palindrome, it can be even or odd, it doesn't matter. But the important thing is that you have something like that. 1, S, 1, then what?
0, S, 0.
Very good. 0, S, 0. Oops. Or?
0, what?
Sorry?
Empty string.
Empty string is right. Well, we will put it in the end. We miss two things. Well, I think you said it though. It's 0 or 1. Yeah. Right? Meaning that, okay, we do the parse tree. So S can be, I don't know, 1, 1, let's say, okay? And then S, recursive, and then let's say, again, 1, 1. And then let's say S, yes. S and then maybe 0, 0, right? And then either the empty string, or a 0, or a 1, it doesn't matter, okay? This is a palindrome, because you have 1, 1, 0, 1, 0, 1, 1. If you read it on the other side, 1, 1, 0, 1, 0, 1, 1. Okay? So this is a grammar for palindromes. You cannot do palindromes in regular languages, you see? This adds a lot of power. Oh, this is nice, the empty set. So your grammar generates the empty set. What's a grammar for the empty set? So it doesn't generate anything. What would you advise? I don't think you can do it. I don't think you can do it. Because it's like you're saying it produces something, right? So my guess was, I looked on Stack Exchange in the end, so my guess was something like this. This is the only rule. You keep producing S, you never reach a terminal. By the definition of grammar, you don't have to reach a terminal really, so it's good with the definition. It doesn't break any rules. It doesn't create the empty string. It doesn't create anything, right? But on Stack Exchange, someone had another option, which is just nothing. The empty grammar. You don't have any rules. So it's an interesting game. It's not really useful in real life. So we saw grammars. On the next lecture, we will see PDAs, push-down automata, and this will be the machine, which will give us more computational power than DFAs, right? So with these machines, what we do is we take DFAs, we add a stack, I said in the last lecture that a stack is first in, first out. It's actually not that. Yeah. But what I meant is that it's
First in, last out.
first in, last out. Yeah. It's like a stack of plates, right?
Or last in, first out.
So last in,
First out.
Which is the same.
last in. Or first in.
You can say it in like 2 or 3 ways.
It's first in, last out.
First in.
Or last in, first out.
Yeah.
Yeah, first in, last out, right? Because you need to. So we add memory. We add this stack memory to DFAs, and we get PDAs, and these are much more powerful than DFAs. They actually recognize all context-free languages. Okay. See you next time.